All right, this video is just to cover the last part of Chapter 18, covering how to compute effect sizes with the ANOVA models. And for the first part, there's actually not any code to look at. There is some material within the course book, and it shows a model with data that aren't available in the book or available for download directly. And so one question is, what is an effect size in a ANOVA model? Um, when you have a t-test, we used as an effect size a standardized difference between means. So you sort of take the means, you divide you divide the difference between the means by a measure of the standard deviation, and so you've got a score between 0 and something very large, and so a value of 1 means it's one standard deviation apart. And so this is sort of uh, a good gauge for how big of an effect you have. For ANOVA models, it's a little different, and we can use our intuition for R squared so, as a basis for this. So, we know that when you're looking at the ANOVA model, like here, we've got this ANOVA model predicting response time by target and foil and their interaction. It has a certain goodness of fit, although, and if we did this with a regression model, it would say what that goodness of fit was in terms of R squared. But the ANOVA model in R doesn't tell us that. It gives us sum of squared deviations and things like that. And so the R squared might be a really good number to start with. Although we don't get it here, we can compute it by hand. So I correlate fit with the actual values, and I can square them, and I get that this has an R squared of 0.25. So that's maybe a good gauge for starting out. I say, well, this model accounts for 25% of the variance. So that's generally what the effect sizes that we compute for ANOVA models will do. They will figure out what proportion of the total variance that we account for is. Notice that we don't even need to know the fitted versus the actual scores to get this value. We can get this because it's the total amount of variance accounted for. We can look up in the sum of squares table. So here's how much the target accounts for, and here's how foil accounts for, and here's the residuals. And so if I take this plus this and divide by this plus this plus this, like I do right here, I get exactly the same number. So that tells me I'm accounting for 25% of the variability in the data. But we can generalize this. So that would be the R squared, and the R squared is a acceptable effect size for the whole test. But we could generalize this, and we can say, well, how much does target alone account for? So I could say target, but then we have to ask, well, what do we want to divide by? Well, target accounts for this divided by this plus this plus this. We divided in the first case by all the variability in the model, and that comes up to 12%. And we could look at foil, and that comes up to 13%. 12% plus 13% is equal to 25%. So we could divvy up how much we account for based on how much each piece is. So this way of finding an effect size is called eta squared. Okay, so Cohen's eta squared computes this. It looks at the sum of the effect over the sum total. That's a really common effect size to compute, and you can do it by hand. There's a couple dozen online calculators that will let you put these numbers in and it'll calculate it for you. I think that's kind of it's nice that you don't have to think about it, but it's nice to sort of know what the effect size is just by looking. You can see, oh, it's going to be this much divided by all of them. So that's eta squared. But sometimes people think, well, that's really not fair, because what we'd actually like is to compute a different number. we want to compute, if we look back up here, let's compute target, the effect size for target versus the effect size for target plus the residuals and ignore foil. So if we can factor out foil, that would give us a better measure of the effect size of target. So it's going to inflate our effect size a little bit with respect to eta squared, but it tells us how much of the stuff that I'm not accounting for by something else like foil am I accounting for. And so this is called partial eta squared, and it's very similar except the number on top in the numerator stays the same, but the number in the denominator gets smaller, so the whole effect size is going to go up a little bit. In this case, it's not really very much because by adding this to the bottom doesn't actually gain us much, but it goes up a little bit. So this is called partial eta squared, and this is how it would be calculated. The numbers would be calculated. A third case says is a little different. It's called omega squared, and this is a little more difficult to calculate. And what it does, it's more like the adjusted R squared that you calculate with R squared. You sort of punish the size of the effect based on the number of degrees of freedom. And so you could, just like in partial R squared or in adjusted R squared, you could have a negative value. And so it's a little more complicated to compute, but you have to take this and you divide by or subtract 13 times like one of these values, and you divide by the total sum of like all four of these parts. So you take the total, the 2022512 is in this table these residual numbers. And this is hard to do and hard to get right just by hand. But here, this is sort of adjusted by the fact that we have a lot of different levels of predictors. So here in this target and this foil, we had 13 different levels of targets and 12 different levels of foils. And so this sort of tries to punish you for having too many things you're predicting. This formula is called omega squared. I found someone who published a version of this on Stack Exchange. The link is here. So you could use this code to quickly calculate it. Here's the actual formula here. And, it's not, but there's also a version, there's a library available called sJstats, and I think it should be updated in this book now, that has a function that let's see, that has a function that lets you compute it. So let's look at this exercise trying to compute. Okay, it's called sJstats. sJstats, when I installed it, it took a while because it had to compile it and everything. So you're going to want to install it on your system, and this might take, let's see if it will install. It's got a set of it's got a function called ANOVA stats, which computes a bunch of different effect sizes. It computes eta and partial eta and omega and omega squared and partial omega squared, I think, and some others that are not here that we haven't talked about, and we'll report all of those about an ANOVA model, or at least most standard ANOVA models it will be able to do. So if we load this, let's look at how to compute effect size for the tooth growth data. So as before, I'm going to change dose to a factor, and I'll just add it to tooth growth and call it dose 2. And then I'll build an ANOVA model, and we can look at the this. And so if we wanted to compute eta for supplement, it would be 205 divided by 205 plus 2400 plus 820. So 205 over, roughly plus 2426 plus 820. That should be about 0.059. So that tells us, oh, supplement really accounts for about 6% of the variance. But I could do, in SJ stats, I could do eta squared of this model, AOV to Thay, and it gives me the same number here. But it does it for all of them. It tells me dose actually accounts for 70% of the variance. And if you compute ANOVA stats, it gives me this whole table. Compute a lot of things, the sum squared and the mean squared and p-values and statistics of the F table. But then it computes eta squared, partial eta squared, omega squared, a related thing to omega squared called partial omega squared. So you can see the partial ones, the values go up because it's sort of it's seeing how much of the residual variance is accounted for after we get rid of the other thing. And omega squared, partial omega squared. So omega squared punishes you a little more than eta squared does for having multiple predictors they're using. And then it's got a thing called Cohen's F, which is another test that I've sometimes used this to do power analyses. And then the overall power of the test. So all of this is really handy to have, and it gives you in sort of one fell swoop all of these measures. We could look at again from the perspective of this ultimatum game data. So if we reload this, we'll do this one more time. We've got the ANOVA. Let's see what happens if we do the same model as a linear model, though. Actually, this is smart enough to be able to give us these numbers even in a linear model, a linear regression instead of an ANOVA. And so if we look at what happened here, in this one, this was the second ultimatum game where there was an interaction. We see that, so eta squared, the condition alone accounted for about 18% of the variance. The gender, although it was significant, was less than 1% of the variance. And the interaction was about 8% of the variance, considerably larger than the gender alone. So although this was, was close to not being significant, but it was significant, it still tells us, it was statistically significant, but it's maybe not that meaningful. And all of these adjusted versions don't increase that or don't elevate that much at all. So interpreting these eta squareds or omega squareds, they're all sort of interpreted the same way. It's just whether you are ignoring different parts, either ignoring other things you can account for, that's the difference between the full and the partial, or sort of punishing you for having multiple predictors, which is the eta versus the omega. Even in this case, condition, this is about 20% of the variance depending on how you're measuring it, 18, 17, 19, 20. And so you might consider, there's 80% of the stuff in your data that you're not actually accounting for yet. All right, so those are effect sizes with in ANOVA. They're easy to calculate by hand, but they also can be calculated with a function in the SJ stats library or a set of functions there. All right, so that's sort of a last little addendum to chapter 18.